Welcome to the Cal Corporation's series of videos about software engineering. The topic of this video is template metaprogramming that computes a type. Before proceeding, make sure that you have already watched these other videos first. Although template parameters are usually placeholders for some type, the previous video showed that they could sometimes be placeholders for some value, such as some integer value. Notice that we're doing it here again, where this is underscore t1 is a placeholder for a Boolean value. However, in this case, is underscore t1 is a dummy template parameter. We're never actually going to use is underscore t1 anywhere. We've only programmed it because of its ability to have a default value. That default value gets evaluated at compile time. Fortunately, both size of double, size of int, and their greater than comparison can all be done at compile time. Our previous video demonstrated a template metafunction, which had computed a value at compile time. Other template metafunctions, like the ones in this video, can be programmed to compute a type. The previous video's result had been in the form of a static data member named value. This time, the result will be in the form of a fully qualified type alias named type. Because the size of double is greater than the size of int on our system, we want the result of our metaprogramming to be the type double. So that's what we cause the type alias named type to be. This metaprogramming only becomes useful when we consider the alternative. When we compared double greater than int, that dummy template parameter is underscore t1 defaulted to true. For the alternative, we can also program a custom implementation of this dummy class bigger for when that third template parameter instead would have defaulted to false. One example where that would have defaulted to false is comparing short greater than int on our system. This alternative implementation simply produces a different answer for its meta computation when it defines the type alias. Template metaprogramming could input and output a whole collection of types as a combination. The best way to manipulate a collection of types at compile time is to mimic the Lisp programming language. So we define this cons template, which has two type aliases. Its first one is called car, and its second one is called cooter. Having that lets you express the combination of two types put together, and then later you can break that up back into one or the other of the two original types. The Lisp programming language would represent a collection of types as a kind of linked list of these conses. For each link in the chain, its first part, the car part, is just a list item, which is the name of some type. Its second part, the cooter part, recursively is the next link in the chain. Eventually, This Lisp collection needs to get terminated by having defined some kind of special terminating type. We've just seen how the Lisp programming language expresses its data recursively. It also processes that data recursively. So now let's use this example collection of types as input to a new C++ template meta function, which we will call biggest. The goal of biggest will be to recursively scan through all the types in this input collection and compute which of those types consumes the most space in memory. Let's first program how that recursion should terminate. In the terminating case, biggest is being specialized by a cons whose could/or part is the special terminating type. For our sample input, that would be when the processing eventually reaches cons unsigned char null. Now, the largest of only one possibility trivially is that one item itself. So this implementation computes that type name, which is in its char placeholder. The other specialization that we care about is the general case, when the could/or part is not the terminating type. Consider the case where cons char could/or specializes to our full input. So then char is short, and could/or is a recursive Lisp expression having int and unsigned char. If the answer we seek is somewhere within the recursive int and unsigned char part, then we'll find it if we do a recursive computation on that could/or. Otherwise, the answer we seek might be the short type that's in the char. So we should compare the char, compare it to the could/or's recursive result. To make that comparison, reuse the bigger metaprogramming from our previous example. Don't worry too much about this extra type name keyword. It merely lets the compiler know that the code following it will express a data type for those rare situations like this where that isn't already guaranteed by the C++ syntax. Whichever one is bigger, char or the recursive result, that's what we need to use as our answer to this step. By the way, there's another equivalent way to express this same recursive logic using class derivations. There are some libraries that would enable a programmer to use their data structures in place of our Lisp-like collection of types. But those libraries would need to be added on instead of being a part of the C++ language itself.